Welcome to a brief presentation of the FHAST model Fish Habitat Assessment and Simulation tool. My name is Peter Dudley. I'm a researcher with the University of California, Santa Cruz and NOAA Fisheries, and this work is sponsored by the U.S. Army Corps of Engineers. So the anadromous fish life cycle is in a loop. It starts up here with the fish spawning. The eggs then incubate. Juveniles then rear on a river. The juveniles then out-migrate from the river to the ocean where they grow. Once they reach maturity, they migrate back up the river to spawn again. The cycle continues. This model looks at the riverine phase of this, so everything except this bottom left box right here, and the effects that habitat alteration or restoration can have on those. Let's look at some of the general principles of this model now. So the model is designed to be useful for managers. What does that mean in practice? It means it has a graphical user interface. It has usable parameters, so the parameters aren't sort of black box objects like dam models or forest models. They're mostly just things like regression. The inputs are spatially explicit, so managers don't have to translate GIS files they might have, for example, into indexes or things like that. It allows you to do A/B comparisons between decisions you need to make and gives you results that are actionable, allowing you to choose between a decision, for example, B1 or B2. It is spatially explicit, as I mentioned before, because habitat restoration or alteration is inherently a spatially explicit thing. The model is mechanistic, allowing you to sort of go outside historical ranges, so not relying on statistics. It has a consistent framework across species with changes in the parameterization and some calculations changing between species, but model structure remaining consistent. All these things make the model expandable to other species or systems, provided that those species or systems at least conform to the general structure of the model. Let's talk a little bit about the framework very briefly. The general framework of the model is to take inputs of habitat, map them onto a grid, and then simulate fish behavior and physiology interacting with that habitat on that grid, resulting in information about energy expenditure and mortality risks, basically resource and death on the river. The grid is made by the user. The user in a GIS program will simply draw a line down the center of a river of interest. They'll then input two parameters into the graphical user interface, one being the resolution of the grid, the other being the lateral extent the grid covers from the center line of the river. Other habitat files can be input either as tables of just simple numbers, such as food density, or, for example, maps, like this example of a cover map, which has vegetation, wood, fine, sediment, gravel, sediment, cobble, and rock. That's then put into the program as a GIS file and then projected onto the grid for the later simulation. Once all those things are projected on the grid, it then simulates fish behavior and physiology, and you get the resulting outputs. So as I mentioned the model is only designed to look at the riverine parts of the fish. Currently, the model has implemented in adult migration, juvenile rearing, and juvenile out-migration. We are actively adding in salmonid spawning and incubation and are hoping to be able to add in green sturgeon spawning and incubation as well in the future. Because this is a high-level overview, I'm just going to give one example of what some of these model components might look like, and that'll be the juvenile feeding model or juvenile rearing model. For example, juvenile rearing is fundamentally the interaction of two things: a risk of predation or mortality from other sources, and also growing large by consuming food resources. Each of these aspects of the model has a sophisticated and mechanistic modeling component to it. So let's, for example, look at drift feeding salmonids. For example, the intake of drift feeding salmonids is modeled as a capture probability times the concentration times the velocity of drift input and the area over which the fish scans and the amount of time it feeds. Each one of these things then has models that are fit based on parameterization from the data. For example, capture velocity is a relationship between velocity of water and the critical swimming speed of the fish, seen here by logistic regression, parameterized for Chinook salmon. Critical swim speed is a function of the length of the fish as well as the temperature, and that can be seen here parameterized for Chinook and steelhead using both temperature parameterization and length parameterization. And so each aspect of the model has sophisticated data and models like that to simulate these things in the system. So every day the fish has to make a decision about based on predation risk and food resources and other risks about what cell to go to. It'll continue to choose a cell on one day and then choose a different cell on the next day, or maybe stay in the same cell, and on until it either suffers a mortality event on the river or out migrates from the river. Let's look very briefly at how it makes those decisions. The fish has two modalities of choosing. Either a fish which is in good physical condition will base its assumption on risks of mortality as well as food resources. Fishes which are in bad health or food physical condition will base their decision about where to go based solely on food. The fish not only chooses the path to go to, or a cell to go to rear, but also chooses the best path selection to avoid mortality, because our model has built-in explicit path selection algorithms in it. So what do you get out of this model? You get lots of different outputs. Here's just an example of a few. For example, a section of the American River where wood in certain areas was about 1% of the cover, and we extended wood cover in certain areas to be 10%. You can then see side-by-side comparisons between the effect this had. Mortality risk decreased as well as was spread out more widely across the river once the wood was added. Note the scales are different here. Predation risk decreased. Again, the scales are different. And you can also see more detailed information that might help explain aspects of this, such as growth trajectories over time of the juveniles in the system. The model outputs lots of data, which managers can then look through in both brief reports and detailed data tables to find information that's relevant for their restoration. So hopefully this has been informative about a high-level overview of the FHAST model. Thank you for your time.